All right, so here is first day of notes. So for a lot of the class, you'll hear me say, just like when we did this in Calc 1, or just like in regular geometry with 2 dimensions, a lot of the stuff that you've already learned is going to pretty much be in effect here. Just we're going to extend it to 3 dimensions, okay? And that's pretty much the theme for our course. All the stuff that you learned how to do about in Calc, we're going to do, but we're going to apply it to 3 dimensions or higher in this class, okay? In addition to that, you'll learn some applications and things where these things pop up, okay? So let's start with defining our 3-dimensional axis, okay? Now, I know engineers sometimes label things differently, but to keep things consistent with mathematicians and our book, we're going to label the x-axis as the one that's coming out towards us, y is left and right, and then z is vertical, up and down, okay? And so, for example, if we wanted to just plot a point, okay, I mean, we're not going to plot points a lot, but just so everybody knows where the positions would be. This is x comma y comma z, right? So 1 would be which direction? Towards you, 1 unit, right. So we're going to go out 1. And then this means left 3. And then now this 5 means from here up 5 units. So this is where 1, -3, 5 would be. Okay, so if you imagine coming out, going left and up, that's where the location is. Okay, you could even imagine this as being the corner of a box, if it helps visualize. Okay, so you can kind of see where it is positioned. Okay. Any questions on just that basic setup there? Okay, let's talk quickly about distance formula. In 2 dimensions, you already know it. Hopefully everyone remembers it. Okay, and it's actually pretty nice. In 3 dimensions, it's what you would expect it to be. The only difference is that you have what? Yeah, you have a z part of it now. So instead of just these two, x1 minus x2 squared plus y1 minus y2 squared plus z1 minus z2 squared, that's the added piece there, the added component. Okay. Now, we're going to go ahead and prove this formula. I mean, it's a nice assumption to make, but one of the things that you'll see in a lot of college classes and that we're going to do, we're going to derive and prove and make sure that you guys understand where things are coming from a lot of the time. You may be even asked on certain exams to do something like similar to that, okay? But here's a quick explanation for why this formula actually works, okay? So if you start by drawing a box, and let's say you label this top left corner, that'll be our x1, y1, z1. and then let's label all the way across and down back right corner. Let's label that x2, y2, and z2. Now, if we're trying to derive the distance formula, then you could argue that, well, really what we're trying to do is find this length from top left corner to back right corner. Okay. Do you guys see anything that we could do, any triangles we could create that might help us along the way? Get a different color here. Yes?
The diagonal from the bottom. So like the one that's right under x1, z1.
From here?
Yeah, to x2, z2.
To here? So if we draw this triangle in, and now what's the other edge? Just this one here? So there is a right triangle that we could use to maybe find what that hypotenuse is going to be. If we know the length of the hypotenuse, that's our answer to the distance question, right? So using these coordinates only, this to this, what's the only variable changing here? So let's call this L1 for the time being. What would L1 be then if it's just z that we're looking at? Very good. So that takes care of that leg. And now this one, well, that one's going to be L2. And that's going to be done the traditional way. Okay? So these 2 points are actually very well chosen because you can imagine that there's no z changing here whatsoever, right? It's just a normal two-dimensional system where here we really have x1, y1, and then no z at all. And then this is same thing as x2, y2. So we could just argue that L2, you can find that length just like you would normally with the distance formula, or if you make a right triangle and do Pythagorean theorem. Does that make sense to you guys? So that would just be the square root of x1 minus x2 squared plus x, whoops, that should be a y1 minus y2 squared. And so now let's label this d. This is the distance that we're trying to find, that top left to bottom right diagonal. Then you could say that distance should be leg 1 squared. Well, leg 1 squared is z1 minus z2 squared. And this will be all in a square root. Plus, and now this leg, L2, well, that's just going to be this radical squared. So we're just going to get those two pieces that we needed, right? So slightly different order. After you square, the square root goes away, but you can see that all three terms we needed are there. Any questions on that? Okay. Then just some added things, and then we'll talk about some graphing here. But so in 2 dimensions, what was the equation for a circle? With radius r and center at x naught, y naught, z naught. Whoop, getting ahead of myself. X naught, y naught.
X squared plus y squared plus r squared.
That's if it's centered at 0, 0, right? If this is the center, then it would be x minus, but yeah, you have the right idea. X naught squared plus y minus y naught squared, which is just the direct product of the distance formula. Okay. Well, Well, in 3 dimensions, instead of a circle, now we would have what? A sphere. And it's going to be identical to this, just like what we did before with the added z minus z naught component. So r is still the radius. Center is now x naught, y naught, z naught. And so we get x minus x naught squared plus y minus y naught squared plus z minus z naught squared equals r squared. Okay. And added one more thing before you guys try an example real quick. Midpoint formula is exactly what you would expect it to be. I don't know if you've ever thought of it this way, but in 2 dimensions, it's really just the average of the coordinates, right? That holds no matter what the dimensions are. So if we have 3 dimensions, how would I find the midpoint of 2 points? Let's say x1, y1, z1, and x2, y2, z2. What would the midpoint be? Yep, so you do x1 plus x2 over 2, and so on. So far, you're seeing things that you've seen before, but just extended to 3 dimensions. Okay. Any questions so far? Okay, then why don't you guys try this problem here real quick. Find the center and radius, whoops, can't spell today, of the sphere x squared plus y squared plus z squared plus 8x minus 2y plus 10z plus 19 equal to 0. So just take a minute, see if you can figure it out. Crystal really doesn't have a partner today, but that's okay. You guys can talk if you have ideas. See, a lot of you are on the right track. That's good. If you don't know where to begin, clearly this is not in the form that we want it to be in, right? We can't just look at that and say, here's the center, here's the radius, but there's something you can do to it. Put it in that form. Right now, I'm just going to write down what I see a lot of you have already written. It looks like a lot of you are grouping your x's together to start, right? So I'm going to go ahead and do that. And now what do I have to do in here? Complete the square. Yeah, you want it to be a perfect square here. So how do I do that again? Divide what by 2 and square it? Okay, so the middle coefficient, cut in half, squared, 16. And you pretty much do that with every single variable. So y squared minus 2y, what would I add in here? That's just 1. And then we got z squared plus 10z. This would have to get 25 added in there. On the right-hand side, we'd move the 19 over, so it's negative 19. And now all these extra numbers that we added, 16, 1, and 25, that gets added to the right. So that's 17, what is that, 42? Please correct me if I'm wrong, because this is going on YouTube. Don't want that mistake. So this should be x plus 4 squared, y minus 1 squared, plus z plus 5 squared equals 23. So the center is negative 4, 1, negative 5, and the radius is root 23. Does that make sense? Okay. Then real quick, the last thing that we'll do today is talk just about cylindrical surfaces. Okay, and cylindrical surfaces, I'm going to really shortchange the description. So if you want to read thoroughly in the book like how it's described, or if you want to revisit this video, because I'm omitting some of the details here. In a nutshell, they're just two-dimensional curves that are extruded, which is a fancy way of saying extended, I guess, along an axis. Okay? So basically every two-dimensional graph that you guys have done can be graphed in 3 dimensions, and here's why. Imagine a parabola. Here's your typical, y equals x squared graph, right? Well, let's transfer this over into a 3-dimensional system. Now, my parabola is going to look something like that. Does that make sense so far? If not, please tell me, because I know I'm going kind of quick. So take your normal 2-dimensional shape, graph it on the xy plane first, and now here's what we mean by extrusion. What variable are we missing here? We're missing z. That tells us that z can be anything we want it to be as long as x and y still have this relationship that y is x squared. So what that means then is that this entire curve gets extruded upward. And so now we get this shape. And so we get this sheet. It's probably easier if I show you a piece of paper, but here's essentially what we're talking about, right? Here's your parabola in 2 dimensions, right? Looking at it head on. Well, now it's just this. Does that make sense? When we extrude it along, actually, it's this way. When we extrude it along the z-axis, right? Here it is. Okay, there's your parabola, y equals x squared. You extend every part of the graph, so every point gets extruded, and you get that nice, basically I just take whatever curve I have, and I just draw a copy of it above or below, and then connect. And that's how you get the 3-dimensional cylindrical surface. Does that kind of make sense to you guys? Okay. So we're going to run out of time, but I've covered everything just barely today.